So if you take a look at this small group discussion, depending how your small group answered, a lot of small groups say that accuracy and precision are pretty much the same thing. And in the English language, a lot of people use those words interchangeably because they are very similar. But in science, we do have completely different definitions for these. They're both related to how good an experiment is or how good the data is, but they mean two different things. So to help you find the difference, let's take a look at the next slide, and you'll see this dart analogy. Pretty much every chemistry textbook has this analogy in it. So have a quick discussion in your small group about the difference between precision and accuracy. So hopefully you came up with the idea that only the first one is accurate. And how is the first one different than dartboard B and C? Well, dartboard A is the only one where the darts actually hit the target, hit the bullseye. So accuracy means how close we are to the actual answer, or the right answer. When you go back and do the density of water lab, or you do labs later in the year, there's a real answer that we should be aiming for, and the question is, did we get that real answer, or how close to that real answer were we? In letter B, you see that there's a difference between accuracy and inaccuracy. In letter B, they did not hit the bullseye, so they were inaccurate, but the similarity between dartboard A and B is that they were both precise. So that's starting to give you the idea that precise means maybe how close the darts are to each other. They're both precise because the darts are close to each other, whether they hit the bullseye or not. And then the worst case in science would be the last dartboard, dartboard C. They did not hit the target, so they were inaccurate, and they were not close to each other, so they would be imprecise. You could technically come up with a fourth dartboard if you wanted to. So if you put some other darts on this side, maybe some darts on this side, some darts on this side, dartboard D, they could actually be accurate. Now we might see that these darts and that the fact that they didn't hit the bullseye, but if you average them out, and that's what we're going to do with our lab values, if you average these values out with those values, you're going to get some darts in the middle. And if you average these values out with these values, they're going to average in the middle. If you average the top and the bottom ones, they'll average in the middle. The left and the right ones, they'll average in the middle. So again, the average here would be pretty close to the bullseye, so it would be accurate, but those darts are not close to each other. So that would be an example of imprecise. So that's like you got the right answer, but you got the right answer just kind of based on luck, just because the average worked out to be right. So if you take a look at our notes here, hopefully we came up with the idea that accuracy is how close your results are to the accepted value, which would be the bullseye. You obviously can't do this if there is no accepted value. And the way we measure this is called percent error. Percent error, you can see the equation down below there. That's on the back of your periodic table, so you don't have to memorize it. But it's where you take your average. So it's not trial 1, not trial 2, but your average of all the trials. And you subtract the accepted value. That would be the error. If you're under, that would be negative. If you're over the accepted value, that would be positive. And then we don't stop there. You divide by the accepted value, because that'll give you a fraction or a decimal. And then when you multiply by 100, that'll turn it into a percent. Have a quick discussion in your small group. Why would it be more important to create a percent error rather than just stopping with the top and measuring the error? Because if you do what the top of the fraction says, that would give you error, but it wouldn't be percent error. Why would percent error be better than regular error? So depending on your small group discussion, you might have come up with the fact that when you compare it with the accepted value at the bottom, it gives you some perspective. A good analogy for this would be a test or a quiz. If you've got 5 questions wrong on a test, would you be happy or sad? And most groups or most students are going to say, well, it depends. What does it depend on? Well, it depends on how many questions there were on the test. So again, if you got 5 questions wrong, you would get a -5. Okay, it would be your test score minus the accepted test score. You got 5 questions wrong. Okay, you would be happy if there were 100 questions on that test. Okay, and why? Well, when you do the math, 100 divided by 100, that cancels out. You'll get negative 5% error. Most people would be happy with a 95% on a test or a quiz. The problem is, if the question or the test is not out of 100, what if the question was out of 10? Okay, that's a totally different scenario. So when you do the math here, 100 divided by 10 would be 10. And if you take 10 times negative 5, that would be negative 50% error. Okay, most people are not going to be happy with getting a 50% on a test or getting 50% of the questions wrong. So again, by turning it into a percent, we're putting it in relative proportion to 100, or we're comparing it to the accepted value. So it gives you some perspective, not just how much error there was, but how much error there was with respect to the accepted value. So a percent error is definitely better than just measuring the error. So now let's take a look at a sample data set. So if you go back to the lab to measure the mass or the formula mass of water, let's say these are your 3 trials results. So you got 17.5, 17.9, 17.8. And the actual answer you should get, if you look at the periodic table, hydrogen weighs 1 or 1.01, and oxygen weighs 16 grams. So if you add that together, because water is H2O, 1 plus 1 plus 16 is about 18. With decimals, it's 18.02 grams. So go ahead and calculate the percent error based on this data. All right, now that you've had some time to take a look at that, you probably realize the first thing you need to do is to calculate the average. So let's make sure we're on the right track for that. So if you take 17.5 plus 17.9 plus 17.8, that gives you a sum of 53.2, but when you divide by 3, my calculator says 17.73333 repeating. Significant? I don't think so. So let's go ahead and write down what our average is, or what our mean is. That's what X bar means, it's the average. Because all of our data points have 1 decimal place, we should probably only keep 1 decimal place in our average. So our average would be 17.7. Now I'm not going to delete what my calculator says. I'm leaving all those digits in there, but when I write down in my formula what the answer is, I'm going to write down 17.7. Now to that, I have to subtract the actual or accepted answer of 18.02. Now I'm going to pause there. We're going to do one step of the equation at a time. So I take my calculator, which already says 17.73 repeating, and when I subtract 18.02, my calculator says negative 0.286 repeating. That's not what I'm going to write down, though, because we just did a subtraction problem. We look at decimal places. 17.7 has 1 decimal place, 18.02 has 2 decimal places. So according to our sig fig rules, I only can keep 1 decimal place. So my calculator answer would round to negative 0.3. Now we're ready for the next step. We divide by 18.02. Again, my calculator still says negative 0.286 repeating, so now I simply type divide by 18.02. And when I get that answer, I get negative 0.0159082501. Again, that's not significant. So now we have to think about sig figs. Because we just did a division problem, now we count sig figs. So we have 1 sig fig on top, and on the bottom we have 4 sig figs. Because we always go with the least number, we're going to round to 1 sig fig. So again, my calculator says negative 0.0159, but if I only get to keep one of those digits, I'm going to write down 0.015 would round up to 2. So it's negative 0.02. The last thing we do is we multiply by 100. That's going to make it 2 digits bigger, so that would be negative 2% error. Quick conversation in your small group. What do you think that negative symbol refers to? Alright, so if you had a chance to discuss that, you probably figured out that it means that our measured average is less than the accepted value. Some teachers have their students put the equation in absolute value, which you'd always get a positive percent error, but I don't like that because the negative 2% error tells you you're below the right answer. And on a lab report where you have to analyze your errors, talk about your error and figure out where that error came from, the fact that you're below the real answer is going to help you figure out where that error possibly came from. Alright, now if we take a look at the second big vocab word for the day, that's precision. And from our dart analogy, we notice that precision is how close the data is to itself or to each other. It's how far the trials are above or below the average. It's your consistency, your repeatability. So you're going to do a density of water data analysis lab where you're going to try to pick the most precise instrument, but we're going to see some instruments that aren't so great, and that's going to help us out by figuring out what equipment we want to use in the future. In chemistry, we always want to perform 3 trials to see if our data is consistent. Although if you're dealing with animals or bacteria or at plants, anything living, I would do at least 10. And in real scientific research, to be statistically significant, you probably need at least 20 trials. And if you realize that one of your trials is not consistent, if you know that you did something wrong, you should probably throw out that data if you know you made a mistake and complete more trials. Alright, hopefully you don't find this poster too offensive, but these are like motivational posters, but it's on despair.com, and these are called demotivational posters. So consistency, what's the definition, or what's the tagline? It's only a virtue if you're not a screw-up. So again, this is getting at the point of the difference between consistency and precision versus accuracy. So this dart, or this arrow analogy, they're very consistent. They were so consistent, they split the second arrow in half. The problem is they were not accurate because they should have been hitting the bullseye, just like in Robin Hood. So let's go ahead and take a look at these 2 trials, or these 2 experiments of data. So we've got experiment A and experiment B. Quick conversation in your small group. Just with a gut feeling, which would you say would be more precise? Alright, most groups are probably saying that experiment A is more precise because the data is closer. You might have just kind of taken a look at the highest number and the lowest number. So you've got a difference between 0.36 versus 0.58. Whereas in the second experiment, experiment B, if you take a look at the lowest number and the highest number, 0.12 versus 0.75, experiment A would be more precise. Okay, what you're really calculating is the range, which is the maximum number minus the minimum number. Okay, you've probably been doing that since elementary school or middle school. The problem with range, and you probably talked about this in math, is that an outlier would really mess up your data. So if all of your data is close, but one number's high and one number's low, that's going to give you a big range, even though most of your data is very close together. So we need to come up with a better way of measuring this, and to do that, if you take a look at the next slide, we've got instructions on how to do standard deviation. So you could technically do this calculation by hand, but it's going to be pretty easy to use a calculator to get the standard deviation. So let's take a look at our data. If you plug our data in to a graphing calculator, according to those instructions, you're going to get an average or a mean of 7.46. And the other number we really care about is the S sub x. That would be the standard deviation. And on this one, you'd get a standard deviation of 0.11. For the second experiment, experiment B, you're going to get the same mean. You're going to get the same average, which is 7.46. But this time, the data is a lot farther off from each other. And our range proved that. But this time, if you take a look at the calculator screen, you get a standard deviation, I think close to 0.3. Let's take a look. Yep, it's 0.32. So again, this is proving that experiment A is a lot tighter, the data is a lot closer together. Now again, if we've taken the effort to come up with standard deviation, we should probably draw a picture to help us understand these numbers a little bit better. So the picture that we use for this would be standard deviation. So this is just a plain old bell curve. So for any time I ask you to draw a picture of standard deviation in a bell curve, you're simply going to sketch out something that's in the shape of a bell. And what goes in the middle would always be your average. So you just write that number there. And then what standard deviation looks at is where is most of our data located. If you go one standard deviation above, so if we add one standard deviation and we subtract one standard deviation, you'll be in the green region, and that would be where 68% of your data is located, where most of the data is located. It's not going to be the range, it's not going to contain all of our data, but it's going to contain most of our data. If you'd want a second standard deviation, if you go 2 above or 2 below, that would be about 95% of your data. And if you add a third standard deviation above and below, that would be about 99 or 99.9% of your data. So let's go ahead and sketch this for our 2 example problems. So we draw a bell curve. We simply put the average in the middle, which was 7.46. And then we're going to draw one standard deviation above, 0.11, and one standard deviation below, 0.11. And we go up, and again, by definition, that's about 68% of our data. Now let's actually get what those values are. If we go 0.11 above 7.46, we'll get 7.57. And if we go 1 below, that would be 7.35. Again, not all of our data is going to fall within that window. 7.36 falls within that window, but 7.58 is too high, and 7.45 falls within that window. Again, about 2/3 of our data, by definition, falls within that window. As comparison, let's take a look at experiment B. We'll get the same average of 7.46, but this time we need a lot bigger of a standard deviation to see 68% of our data. This time we're adding 0.32 above and 0.32 below. So to see the same 68% of our data, we're going to have a lot bigger of a window here. So if you put the max and the min for that window, if I go 0.32 above, that would be 7.78. And if I go 0.32 below, that would be 7.14. Again, not all of our data will fall within that window. 7.12 is going to be too low, but 7.52 would fall within that window, and 7.75 would fall within that window. So again, about 2/3 of our data would be within that one standard deviation range.